Now let's move on to a very important topic, the next section basically, which relates to the errors in measurement. So before we understand what kinds of errors are there in measurement, let us visit a very important concept, which is accuracy versus precision. So what do we mean by those two terms, accuracy and precision? See, when I'm doing an experiment, I'm not doing a single experiment. When I'm not taking a single reading, I would do the experiment multiple times and I would take several repeated measures of the same quantity. In those, across those repeated measurements, what I can be accurate and I can be precise. So here is an example which gives the same concept in terms of the dartboard. So in case of a dartboard, our objective is to really come as close as possible to the center of the dartboard. So that is what we are trying to do in the case of measurement also. Our objective, when I am measuring this, for example, this particular remote, my real objective is to come as close as possible to the real length of this remote. That is my ultimate objective. A dart thrower, a person who is throwing the dart, is very accurate if he is able to throw the dart at the center of the dartboard. So that is the very simple definition of accuracy, and that is actually the correct definition. That if a person is able to throw the dart at the very center, then he is very, very accurate. Now, when he is doing the repeated throwing of the darts, if his darts land close to each other, then he is also very, very precise. So those are the distinctions. When across different throws, if his darts end up at the same point, then he is very, very precise. Now, if those points, the 4 points in this example, are very far from the center, okay, but close to each other, then his measurement is very precise but not very accurate, because he is not throwing towards the center. If his 4 darts, if he did this experiment 4 times, if he threw the dart 4 times, if his darts landed up in the center and were also close to each other, then his measurements were accurate as well as precise. So B here is not accurate but precise, okay, but not accurate. D here is accurate as well as precise. Now let's go on to the example C here. In C, what has happened? He has thrown the darts all spread across the entire board. If you take the average of those readings though, those average would end up being very close to the center. So although he was not precise, his darts went all over the board. He was accurate though, because the average of those 4 readings was actually very, very close to the real value. So this is accurate but not precise. Okay. And the very first example A here, all the 4 darts are very far from each other, as well as they are very on one side of the center, which means their average would be incorrect. So that this measurement is not very accurate, and they are also very far apart, and therefore his measurement is not precise either. Okay, so that is very, very important distinction between precision and accuracy. See, the precision is basically it comes from how we are doing the measurement. So for example, if I am doing the measurement using my normal ruler that I use every day, those measurements are not expected to be very accurate. They can only be accurate up to 1 millimeter. That is the ultimate that I can get with a ruler. If I am using vernier calipers, then I get actually better accuracy, right? So better precision, sorry. So the precision is very much related to how I am doing the measurement, what instrument I am using for doing the measurement. Accuracy is the result of the overall process of measurement, how I am actually, the entire process of measurement, how it is being carried out. So for example, if my ruler, I make it very, very accurate I'm not only using a ruler, I am using some very, very accurate, very, very precise instrument to do the measurement. But that instrument has a 0 error. There is error in that instrument that it will always be off by 1 centimeter. Then no matter how precise I make it, I can never be very, very accurate. So here is a simple demonstration that we'll do to again give this concept a better feel for this concept. So here is some water. I'll pour into this jar, this measuring flask. This is known as measuring flask. Here are the gradations in this flask. Okay, so we'll just make things a little larger so you can see it. So here are the gradations in this flask. You can see these gradations. Okay, so it's not important that you read this, but the idea is that the process of measurement is I just pour water from this glass onto this jar and I do the measurement. Now, in this process of measurement, no matter how precise, how many gradations I create here in this jar, the process itself is not very accurate. And why is that? Because no matter how hard I try, some of the water will always be remaining inside the glass. So that process itself is designed to not be very accurate, no matter how much precision my instrument has. So accuracy is the result of the entire setup of the experiment, how it is done, and precision is the result of how close my markings are, how much small units, how much precise my actual measurement instrument is. Okay, so the precision is the result of that. So that is the thing that we understand here. Now let's move on to the errors in measurement. So errors in measurement are of course of two kinds. This is not very difficult concept, very simple. There are two basic kinds of errors. One is the systematic error and the second is random error. Random error, as the name itself suggests, means that my error is changing each time I am doing the experiment. So like I said before, typically in physics when we are doing experiments, we don't do it just once. We repeat the experiment. We try to repeat it and just make sure that the readings that we are getting are actually correct. So a systematic error would mean that I am getting the error usually in the same direction, which means that either I am overestimating something or I am underestimating something, and I continue to do so in each of my readings. So that is systematic error. The second kind of error is random error. Random errors change in magnitude as well as direction. That means that they either become positive or negative across various sort of repeats of the same experiment, and they also change in value. Sometimes the random error would be large, sometimes the random error would be low. So here again in our water experiment, like I said, some of the water always sticking in the glass is an example of systematic error. Why is this systematic? Because this would always result in me underestimating the quantity of water. So it's a systematic error, it's always in one direction. Another example of systematic error is zero error. What is zero error? Zero error means that in my scale, if I am using a scale to do the measurement, in that scale, instead of, so here is an example of our zero error. So in the scale, if I am doing the measurement, instead of starting from 0, for some reason I start at 1. All my readings I will take starting at 1. Then in that case, I am creating a zero error. Instead of starting from 0, I am starting from 1 centimeter, and all my readings would be overestimated by 1 centimeter. So that is zero error. Similarly, zero error, where it's commonly observed, is when we are weighing things. When we weigh things and our weighing scale has a zero error, it means that when nothing is put on the scale, then also it shows some weight. So here in this example, we have a scale which shows 2 kg, but if you look here, there is nothing put on the scale. So my minimum reading is 2 kg. To remove this zero error, this is a systematic error like we said. What do I have to do? I have to take the reading and then subtract my zero error. The error which is there from the beginning itself. When it was supposed to read 0, the scale read 2 kg. So now if I put anything here and I weigh it and my reading comes out to be 100 kg, then I have to subtract this 2 kg from 100 kg to get the real reading. So my real reading in this case would be 98. If I, instead of measuring from 0 centimeter, if in the scale I am measuring from 1 centimeter, then from my reading I have to subtract 1 to get the real length of whatever I am trying to measure. So zero error is a very good example of the basically a systematic error. Another example of systematic error is when a person is taking the reading. For example, when you are reading the scale, then you always lean on one side. You always lean on one side and then read the scale. So you know that when we lean on one side and take the reading, then we get an error known as parallax error. But if I lean only on one side, then my parallax error would always be either positive or negative. It would always be either positive or negative. That is not something that we typically want. Okay, but this is an example of systematic error. When we lean in one direction and when we create parallax always in all the readings in one direction. Okay, so systematic errors can both be due to instrument. In zero error is an example. The second is personal. The doing parallax error only in one direction is an example of that. When the systematic errors are personal, they are also known as bias error, because in my measuring technique, I am biased toward one side. For example, my right hand side is strong, so I always lean on right hand side. Okay, if for example I have during playing a game or something, I have just hurt my right hand or my neck. If I cannot turn in this direction, then I will always lean in this direction and take the reading, and that would create a bias. The bias is personal, so but it is a systematic error. Now, another example I gave you of systematic error is our entire process can be flawed, and this would result in systematic error in one direction. For example, our water example, that if some of the quantity that we are measuring sticks to the surface of things, then I create a systematic error in which I am always losing some quantity before I measure it. Random errors are typically, like we said, they are unpredictable. Okay, and they can also be personal. So for example, if I am doing the parallax error, but I change the side of measuring, sometimes I view the scale from the right, sometimes from left, sometimes from right, sometimes from left, then I am creating a parallax error, but this parallax error now becomes random error. Instead of being a systematic error, it becomes a random error, because sometimes I will be overestimating the reading, sometimes I will be underestimating it. Another kind of error which is always present in all the measurements is actually least count error. What is least count error? Least count errors is the inherent limitation of our instrument. So for example, if I have a scale which has 1 millimeter gradations, then I cannot be expected to read more accurate than 1 millimeter. So that 1 millimeter is the least count error. That amount of error is always present in my measurements using the scale which has 1 millimeter gradation. So let us look at some of the characteristics of random error. See, the most important thing here in terms of random error is the random errors are very closely related to the concept of precision that we had discussed in the first slide. The higher our precision, the less the chances of making random error. For example, if I use vernier calipers instead of normal scale, then I am reducing my random errors. Systematic errors cannot be eliminated just by increasing the accuracy of our instruments. If I instead of using this particular measuring jar, if I use a measuring jar which has many more gradations, very accurate, but if I continue to lose water in other instruments, when I in this measurement, if I don't pour all the water, if I am not able to take into account all the water when I pour it in, some of the water is always remaining in this glass, then my systematic error would always be there. So systematic errors have to be corrected across the entire process. For example, another example of systematic error is zero error. If your instrument, no matter if it is very precise, but if it has zero error, that amount of error has to be corrected for. Okay. Another thing about systematic errors is sometimes systematic errors, like we said in the case of zero error, they are constant. Other times the systematic errors actually drift. They change across time. One such example is when you are doing readings, experiments using ammeters and voltmeters. When they are put in the circuit, the ammeters and voltmeters, they heat up. As the instruments heat up, they start drifting. Their readings start drifting. So initially, when you started doing the measurement, the experiment, when you did the first experiment, the first reading, when you took the first reading, it was very accurate. Everything was fine, and your reading came out to be very good, right? For example, you were able to read the current as 1 ampere. In the next reading, just because the instrument heated up, you will the same amount of current, right? The current is still 1 ampere. The current has not changed, but the instrument might show you 1.05 ampere. Okay, so this is known as drift. So drift errors are those systematic errors which happen over time, which change with time. Other thing, okay, so this is what we have discussed. We have discussed the next thing is sometimes the systematic errors are not constant. So zero error that we have seen so far has been constant. Sometimes our systematic errors are actually proportional to our actual measurement. So they can be for example, in the case, especially if the things change, if my instruments, they deviate based on the environmental that I am doing the measurement in that case the errors can actually be proportional to the measured quantity. So a good example of that is if you take a thermometer. Now the thermometer, if it is reading 100 degrees, then its systematic error can be only be 10 degrees. If the thermometer is reading 200 degrees, then it can have an error as much as 20 degrees. So in that case, we say that the thermometer is accurate to within 10%. Okay. So in a reading of 100 degrees, I can get an error of 10 degrees. In a reading of 200 degrees, I will get an error again of 10%, which means up to 20 degrees. So sometimes these systematic errors are proportional. They are measured in percentages, and sometimes they are absolute, right? So those things we have to be careful about. Like with zero error, we have already discussed. Now we come to the important concept, which is the least count. Now least count, as we have seen, we know this is the minimum measurement that I can do using a particular instrument. Ruler is our standard example because we all have it, we use it. The ruler, it has a least count of 1 millimeter. This is a typical ruler. Okay. And the main gradations are 1 centimeter apart. So this is 1 centimeter, and then 1 centimeter is again divided into 10 regions. Okay. Each of these smaller divisions is 1 millimeter. Now when we do the measurement using this ruler, this is how it looks. We are measuring a block. We'll try to report the least count error of this ruler. So if you start from 0 and this reading goes on till, so this is 1, this is 2, this is the gradation halfway between 1 and 2. So this is 1.5. Okay, this is 5, and then 6, 7, 8. Okay, so I can read 8 till 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So till 8 I can read. So the reading is just over 1.8. Now this is where the problem comes. Okay, so this is 1.8 centimeter. Now this is where the problem actually comes. Now how do I write this? I can clearly see that there is this block exceeds 1.8 by a little. I can clearly see it here. So how do I express the fact that I measured till 1.8? That is correct, but I am not sure above it. Okay, whether I want to express the fact that the reading is not exactly 1.8. It deviates from 1.8. Okay, and the fact that fact I write by using. So I will write it as 1.8 by using this convention, wherein I note the error in measurement after the main reading. So I write the main reading as 1.8 centimeter. This I have already written. After that, I say that, oh, this 1.8 I was able to read, but after that I am not really sure what it is. So I write plus minus. So this 1.8 can be above the actual length of the block, can be above or below this 1.8. Now what do I put here? By how much can it be above or below? That is the main question here. See, typically what we will say is that if the reading was closer to 1.8, I would have read it as 1.8. If the reading was closer to 1.9, I would have read it as 1.9. That means that the maximum error that would be there would be 0.05 centimeter. Okay, so 1.8 centimeter plus minus 0.05 centimeter, right? So all this, the error and the reading itself are in the same units. Notice that. Okay, and this 0.05 tells me that I cannot be more accurate than that. Of course, the problem here is that the entire reading length of the block has been measured by subtracting the beginning reading from the end reading. So this end reading has been 1.8 plus minus 0.05 centimeter. This is the end reading, but the beginning reading is also there, and the beginning reading also I am not really sure, right? So I started from 0, I know that, but during the measurement I could have deviated a little, things could have shifted a little, so I'm not really sure. So there is an uncertainty in the beginning also, and that also has to be expressed here, and for that I will write 0.0 plus minus 0.05. So that is my beginning reading, and the net result of this entire reading is what? 1.8 plus minus 0.05. Okay, so this is the end minus the beginning, 0.0 plus minus 0.05. Okay, this uncertainty, note that it is present in the beginning as well as in the end. Okay, and I have to express both, I have to write both, right? Because the beginning reading is also, I am not really sure, I could be off by 0.05. The net uncertainty is, see, the total error always gets added when I am adding or subtracting. That is to be expected, because to get the maximum variation in the net reading, I have to take the maximum value of the first quantity, because there is a subtraction sign here. So I have to take the maximum value here, and I have to take the minimum value here, and that would give me the maximum range of this maximum range of possible error in the measurement of this block. So if I do this, then this becomes 1.8 minus 0, and plus minus 0.05 would be added, and this would become 0.1. Okay, and this entire thing is centimeter. So this is how we report the least count error. So in this measurement, our minimum reading that we could take was 0.1 centimeter, and that appears as plus minus, and then our least count, that 0.1 centimeter our least count appears there. Okay, the thing to note here is how we achieved this least count, because I could be off in my beginning reading, I could be off in my by 0.5 in my end reading. So the net result is that in total I could be off by 0.1 in the entire, when I am measuring the entire length of the block, and that is why we arrived at this 0.1 centimeter as our net error. Okay, so this was the least count error, and this is how we actually report it. So this is very, very important in all your measurements. When you are doing the measurements, this is how you have to report the results. You write the reading, and then you add plus minus the least count of the instrument after that reading, and then you write the unit, whether it is centimeter or millimeter, whatever. Again, we take an example. Here we are measuring the pencil using this ruler. What we do is that we read. So we read 5, and then we read the number of gradations in millimeters. So it's 1, 2, 4, 5, 6. So this becomes 5.6, and again plus minus 0.1, and this entire thing is in centimeter. So we write centimeter in the bracket. So now that we are done with the reporting of these errors, let's look at some of the other errors that could happen. See, one of the errors that we have seen in the measurement was the parallax error. So that could be there, that when we are looking at it from this side, okay, this is our eye, and we are looking at it from this side, or when we are looking at taking the reading from this side, from the other side. If in both these cases, our error would be different, our reading would be different, and this is the parallax error. Bias error, we have talked about, that a person might always read it one way or the other, either less or more. That is again an example of the both of them can be either systematic or they can be random, depending upon whether you shift sides or not. Now here is a way to reduce the random errors. So we can reduce the random errors. By nature they are random, and that is why if we take many measurements and take an average of those many observations or many measurements, then these random errors, by definition as they are random, they would cancel out when we take the average. So to improve your precision of measurement against these random errors, to improve the precision of your measurement against the random errors, take many readings and then take their average. So random errors would typically get cancelled out. Another way to improve your accuracy against random errors is to use higher precision instruments, because the higher precision instrument and higher precision methods of measurement, they inherently have less random error. Systematic errors, I mean, we have to make sure that our methods are not prone to systematic errors. That is the first thing. So for example, if I am measuring certain amount of liquid, I just have to make sure that I pour all the liquid during the measurement. If I am weighing something, I have to just make sure that I weigh everything, okay, that I need to weigh during the measurement. So that is an systematic, that is a way of reducing the systematic error, that we just improve our processes. The second thing is that we have to take into account systematic errors in our scale. For example, zero error, that we have to always take those into account. And the third important method is that we can convert systematic errors to random errors. And then because random errors get cancelled across multiple measurements, we remove those systematic errors. We don't remove it, but we somehow cancel those systematic errors across many measurements. So that's the third way. So for example, as I already told you, if the parallax error, instead of always being on one side, read the instruments from sometimes from this side, sometimes from that side, and that would reduce the that would change the systematic error to random error, and then across the measurements your parallax error would then cancel out. So that is the systematic error. Now here are some other classes that we have taken on similar topic. Out of this, the first one is very important, which is where we understand the negative zero error. What do we mean by negative zero error? So definitely go through these classes as well. There are not many numericals based on these problems. This is mainly a theoretical topic, and this will be covered in your laboratory exercises. So it is very important that you understand this. Thank you.